Welcome back, everyone. In this part of the lecture, we're now ready to graph functions with asymptotes. Here we're going to combine our knowledge of asymptotes, relative extrema, concavity, and the table of signs of the first and the second derivative. Let's start with the guidelines in graphing. These guidelines are similar to the guidelines we use in graphing polynomial functions, but with the additions of asymptotes. First step is to find the domain and intercepts. Next is to find the vertical, horizontal, and oblique asymptotes using limits. We then determine f prime and f double prime, which will give us our critical numbers and possible points of inflection. After which, we construct the table of signs of f prime and f double prime so that we can determine the intervals at which the function is increasing or decreasing, and the intervals at which the function is concave up or concave down. Because of the table of signs, we can also determine the coordinates of the relative extrema and points of inflection. We then plot important points, asymptotes, intercepts, holes, extrema, point of inflection, and use the table of signs to graph the rest of the function. Are you excited to graph rational functions? Let's move on to our first example. Let's sketch the graph of f of x equals x squared all over 9 minus x squared. Note that this example is the same examples we repeatedly use in previous videos. For our solutions, we will first find the following: domain, intercepts, asymptotes, the first and the second derivative, critical numbers, possible points of inflection. For the domain, as you can see, the denominator is 9 minus x squared, and hence our domain is all real numbers except plus or minus 3. The x-intercept, we set y equals 0, and for the y-intercept, we set x equals 0. So we get 0 and 0. In the previous video, we have computed the vertical asymptotes as x equals negative 3 and x equals 3, and the horizontal asymptote is y equals negative 1. You may pause this video and revisit that video to find out how these asymptotes are obtained. Because we have a horizontal asymptote, we do not have an oblique asymptote. Let's continue. Our first derivative, which you can verify, is 18x all over the quantity 9 minus x squared squared. So we have a critical number at 0. Our second derivative is this one. Okay? And we do not have a possible point of inflection. What's our next step? Right. Our next step is to construct the table of signs. Again, we're going to construct only one table for f prime and f double prime, and we will present the table vertically. The intervals will be cut among the critical number, possible points of inflection, and the vertical asymptotes. So here are the intervals. So we cut the interval at negative 3, 0, and 3. Before we move on, let's assign the vertical asymptotes as follows. So since we are vertical asymptotes as x equals negative 3 and x equals 3, put it like this. We have undefined for the f prime and f double prime there, because this is our vertical asymptotes. Nice. For f prime, we know that at the 0 is a critical number, so we have a 0 here. And again, to get the signs at each interval, all we need to do is to substitute a number to f prime in those intervals. Note that for f prime, again, the denominator is always positive, so we only need to check the sign of the numerator. For example, in the interval negative infinity to negative 3, we can take x equals negative 4, substitute here, since 18x, x negative 4, therefore the sign is negative. Great. We can do that in each interval, and we will get negative in the interval negative 3 to 0, positive here, and then positive at the interval 3 to infinity. You may pause the video and try to solve the signs of f prime using the method I mentioned a while ago. Alright, let's continue to f double prime. It's the same. We need to substitute a number on the interval and check whether f double prime is negative or positive. Okay? You can pause the video and try it on your own. You should get the following. So we have negative here, positive from negative 3 to 3, and then lastly negative 3 to positive infinity. Nice! We're done with the table of signs of f prime and f double prime, and we move on to the conclusions derived from these signs. Okay. On the interval from negative infinity to negative 3, since this is negative and this is negative, hence we have decreasing concave down. Next, negative 3 to 0, we have negative positive, and therefore we are decreasing concave up. Nice. Next interval, 0 to 3, positive, positive, and therefore increasing concave up. Okay. So as you can see here, we have a decreasing to increasing, a change in the sign of f prime, and therefore at x equals 0, so later we'll see at x equals 0, yes, this one, we have a relative minimum at x equals 0. Now for the 3 to infinity, since this is positive and this is negative, we are increasing concave down. Alright, so since now that x equals 0 is a relative minimum, we substitute 0 to our function to get the point 0. Nice. Now we have the following points, 0, 0, which is our intercept, and also a relative minimum. And we have now the asymptotes, y equals negative 1, x equals negative 3, and x equals 3. We are now ready to plot the graph of this function. Our first step is to plot the points, important points, and the asymptotes. So here are our asymptotes. The horizontal asymptote y equals negative 1, the vertical asymptote x equals negative 3, and the vertical asymptote x equals 3. Great. Now we plot the point 0, 0. For the rest of the graph, we only need to check the conclusions now in the table of signs. Okay. For the interval from negative infinity to negative 3, it is decreasing concave down. So on the left of x equals negative 3, we should be decreasing and we should be concave down. So how is it? Can you think about that? It should be decreasing, so it should be from the left going down, but it should be concave down. And likewise, since we have asymptotes, it should get closer and closer to x equals negative 3 and y equals negative 1. The only possible graph is this one. Okay? Decreasing, concave down. Get it? Nice. Decreasing, concave down. Approaching the horizontal asymptote y equals negative 1 and approaching the vertical asymptote x equals negative 3. Did you get it? Very good. Now, on the interval -3 to 0, we are decreasing concave up and must pass 0, 0. So we can only have this part. Decreasing concave up must pass 0, 0, must be asymptotic to x equals -3. So everything is okay. Now for 0 to 3, it should be increasing concave up. So we're going up and concave up. And then we should go near the vertical asymptote x equals 3. So we get this part of the graph. Great! Lastly, for the interval 3 to positive infinity, it is increasing and concave down there. And therefore, we have this part of the graph. So increasing concave down must be asymptotic to the vertical asymptote x equals 3 and must approach the horizontal line y equals -1. Nice! This is the graph now of our rational function x squared all over 9 minus x squared. Very nice. We have graphed this function analytically using our previous knowledge. Very good. Let's move on to the next example. In this example, we want to sketch the rational function x cubed plus 4x squared minus 5 all over x squared minus 1. Again, this is the same as in the previous examples in previous videos. So you may verify and check our previous videos if you have questions on the solution. Nice! Our first step is again to determine the domain, intercepts, asymptotes, first and second derivatives, critical numbers, and possible points of inflection. The domain of this function is of course all real numbers except plus or minus 1. So minus all real numbers except -1 and 1. The x-intercept, to do the x-intercept, you just set y equals 0, solve for x. You should get these values. Okay? So you may pause the video and try it on your own. Next, for the y-intercept, you set x equals 0 and you should get the y-intercept to be 5. Nice! In the previous video, we have shown that the asymptotes, or there is a hole in 1, 11 over 2. There is a vertical asymptote at x equals -1, an oblique asymptote at y equals x plus 4, and we do not have a horizontal asymptote. The first and the second derivatives of this rational function are shown. Okay? Because this is our first derivative and this is our second derivative. The critical numbers are 0 and -2. Okay? And we do not have a possible point of inflection. Nice! Let's move on. The next step is again to construct table of signs for f prime and f double prime. So the intervals are as follows. So note that we have cut the interval along the critical numbers and the vertical asymptote. Okay. So we then label the vertical asymptote. So since the vertical asymptote is -1, we label it first. So undefined, undefined, undefined vertical asymptotes. Okay. Then for our f prime, critical numbers are 0 and -2, and therefore we have 0 here and 0 there. Nice. So we just need to check the signs at each interval. How do we do it? We again substitute some values on the interval to our first derivative. To ease the computation, again, you can check that the denominator of the first derivative is always positive. Okay, so for example, negative infinity to negative 2, we can substitute x equals negative 3. If x is negative 3 here, x is negative 3, so this is negative. If x is negative 3, this is negative as well. And then for negative, negative, positive, we get positive. Alright, so I will do one more. So from negative 2 to negative 1, okay, negative 2 to negative 1, what value of x? We can check the value negative 3 halves, okay, or negative 1.5. If we substitute negative 1.5 here, so negative 1.5 is negative, negative 1.5 plus 2 is positive. So therefore we have a negative and positive, and hence f prime has a sign of negative. Did you get it? You can solve as well for the two remaining intervals, substituting a value inside the interval. Nice, and you should get negative here in the interval negative 1 to 0, and then positive now on the interval from 0 to infinity. For the signs of the second derivative, we do the same method. So again, we plot or we substitute some points inside the interval and get the sign of the second derivative. Okay? So you should get that on the left of negative 1, it's always negative, and on the right of negative 1, the second derivative is positive. Great. So we're now moving on to the conclusions from this table of signs. On the interval from negative infinity to negative 2, positive, negative, and therefore we are increasing concave down. Next, we have from negative 2 to negative 1, negative, negative, and therefore we are decreasing concave down. Negative 1 to 0, we are decreasing concave up because we have negative here and then we have positive here. And lastly, 0 to infinity, we are positive here, positive, and therefore increasing concave up. Nice. Now, since we have changed from increasing to decreasing, hence at x equals negative 2, we have a relative maximum. Great. Since we have a relative maximum at that point, we substitute negative 2 on the function to get the function value of 1. So please verify that f of negative 2 is indeed 1. Nice. Now, x equals 0. Since we have changed from decreasing to increasing, at x equals 0, we have a relative minimum. So we substitute again 0 on our function to get the point. So we have 5. Nice. So we're done with the table of signs. We have now this table. Okay, so from the table of signs here, we just get those that we need in graphing, so the conclusions and the points. So take note that we have a vertical asymptote at x equals negative 1 and an oblique asymptote at y equals x plus 4. So we plot actually those first. So we plot x equals negative 1, vertical asymptotes, and then we plot the oblique asymptote y equals x plus 4. Nice. Now, let's plot the relative minimum and maximum. Those points are the intercepts as well. So here are our intercepts, and this is our relative minimum, and this is our relative maximum. Great. Since we have plotted those points and the asymptotes, we are now ready to graph using the conclusions in the table of signs. First, On the interval from negative infinity to negative 2, we must be increasing and concave down. So from the left of negative 2, which is here, this point is the left of negative 2, we should be increasing concave down and must approach our asymptotes. And also pass the intercept. Okay? So we have this graph. So increasing, going up to negative 2, concave down, asymptotic to our oblique asymptote, passing through the x-intercept. Nice. Now, on the interval from negative 2 to negative 1, we should be decreasing concave down and must be asymptotic to our vertical line, negative 1. We have this part. So, decreasing, going down, concave down, and asymptotic to our vertical asymptote. Next is the interval from negative 1 to 0. So, here is from negative 1 to 0. So, from negative 1 to 0, we are decreasing concave up, but we must pass the point 0.5. We have this part of the graph. So, it is asymptotic to the vertical asymptote x equals negative 1, decreasing and concave up, and passes the point 0.5. Great. Our last interval is from 0 to positive infinity, and we must be increasing, so going up, concave up, and as well must pass the whole, okay? And asymptotic to our oblique asymptote. So finally, we have this part of the graph. So it passes the whole, it's increasing, concave up, and asymptotic to the line y equals x plus 4. Awesome! This is the graph now of our rational function. Very good. That ends this part of the lecture. The next part of the lecture is to determine how to graph a function from the graph of its first derivative. See you on the next video.